So the goal of the presentation is to explain and prove some of the results relating to Abel Jacobi theorem, but even just to state the theorem, there are many preliminary works to do. And so I'll start now. Well, I'll assume some familiarity with Riemann surfaces and notations relating to it. And book I would follow is Introduction to Algebraic Curves by Griffiths. And I'll use some results from Hudson and Griffiths and Harris, like on algebraic geometry. Okay. So our main concern is the Riemann surface. So Riemann surface is topologically Hausdorff and compact. Actually, you might have to say it's compact Riemann surface, but in this talk I'll only talk about compact Riemann surfaces. And with one-dimensional complex coordinations. And on the complex coordinate chart, on the overlap, we want the biholomorphism between them. And from the fact that in the overlap is biholomorphism together with Cauchy-Riemann equation, we know that the compact Riemann surface is orientable two-dimensional real manifold. And on the two-dimensional real manifold, in terms of topology, it can be completely determined by its genes. I'll denote genus as G for the following times. Okay. Now, we need some category of Riemann surfaces. So if you have a map, and in general, it's C union with infinite, and we can consider it as a projective space, P1. And we say F is holomorphic or meromorphic function if in terms of coordinate chart. So if you have coordinate chart, and we say indexed by I, then the induced map making this commutative diagram is holomorphic. So FU is holomorphic. And we define the meromorphic function in the same way. And with this defined, then we, in the category of Riemann surfaces, if you have two different Riemann surfaces, then we say it is a morphism, say F. If you have a small neighborhood, so I'll just denote by UI, so it's locally a holomorphic function, and this map, the induced map, making this diagram commutative, and if the F is holomorphic for every open, or locally for every point, if there's holomorphic extension, then we say this is a holomorphic map. And so the category of Riemann surface is that, so it's a Riemann surface such that the maps are locally holomorphic. Okay. And from this locally holomorphic characteristic actually gives rise to many interesting facts. And one of them is that it looks very simple if you reduce it. So suppose you have a C prime, where this is a holomorphic map, then we know this is Z. So okay, actually, Z is so on the neighborhood, it's not the map, but it's on a small neighborhood such that the Z is a coordinate chart and W is also a coordinate chart. Okay. Actually, Then on a small neighborhood, let's say VP to WQ, and this is the F restricted. Then we have the coordinate chart, let's say, and we make it as simple as possible, where it's a small neighborhood in the complex plane. And we want it such that Z of P equals W of Q, and this is just by n equal 0. So we have an induced holomorphic map. Let's call it F triangle. Okay, now so locally it's a holomorphic function where it sends 0 to 0. So it can be classified in terms of multiplicity of 0. So we can express F delta as Z to the mu and H Z, where mu is strictly positive and H0 is not 0. And from this, some with analytic results, there exists a square root mu of F delta, and it can be denoted computationally as Z, let's say A1 delta D squared. And together, and one thing you should notice is that the first derivative is non-zero, and with the holomorphic inverse function theorem, this is a biholomorphism. Okay. So what we have is biholomorphism, and this is F delta square root mu, and we have another delta. And although this definition of the square root might be smaller, but we can just shrink the domains altogether. And this is a biholomorphism. Then the induced map here will be just e to the mu, making this commute. So because of the holomorphic property, holomorphic property locally just looks like a power. And we define the ramification index, which is mu minus 1. So mu minus 1 is a ramification index near P of this morphism. One remark is that in this neighborhood, it looks like mu to 1 map, although it's not, like, for example, on the origin it's 1 to 1, but with multiplicity, it looks like a mu to 1 map. That's one remark. And now we'll talk about holomorphic differentials and meromorphic differentials. Sorry. 1. This is number 1. And we also define this in terms of coordinate charts. So we say Wi is holomorphic or meromorphic differential if it can be written as a locally meromorphic function. We satisfy that on the overlap, it should satisfy this equation. J should equal to Fi J. So Cij is the biholomorphism from the J in the overlap from J to I, and this is one thing you can notice is that it represents the change of variable when we integrate, and actually this will ensure that if you integrate some meromorphic or holomorphic differential, like through the path gamma, then it will be defined by sigma, where gamma I is a disjoint partition of gamma such that gamma I is also a smooth path and is completely contained in one of the local coordinate chart. And so not the other way. This will be. You can check this is well defined by intersecting with gamma j and then with sigma. Suppose gamma j is another partition, then gamma prime j, then we take the sigma, then we change the sigma sign and use the change of variable equation. Then we get no matter how the partition is done, the value will be the same. So this is how the integration is defined. One remark from Stokes' theorem is that suppose omega is defined on an open set. This is open set. Then if you integrate on the boundary, then this has to be. As a corollary, I'll talk about the corollary later. Later on, we will talk about divisors, and divisors is something classifying points on the surface. Something represents points. So, and the important kind of divisors are the divisors arising from meromorphic functions or holomorphic or meromorphic differentials. So we define multiplicity. Suppose f is a mero or holomorphic. Then we define the multiplicity at p in terms of coordinate chart. So suppose this locally near P can be represented as Z to the Z to the mu, and we see where Z is not 0, then we say mu is so if F locally so some open set locally represented by this, then we say B P of F equals mu. And with the holomorphic differential or meromorphic differential, we'll define the same way using the local function. And you'll see that this is well defined on the overlap since this is a biholomorphism, and necessarily the derivative has to be non-zero. And that ensures this is well defined. So, yeah. One corollary of this Stokes' theorem is that if you consider D over N, then it has finitely many singularities. So what we can do is, near the singularity, we punch a disk, then we get an open set. Then if you integrate along the open set, we get this, and this by Stokes' theorem is 0, but this is also equal to the sigma and VP. Later on, we'll also talk about differential forms. So when we talk about differential forms, we'll be viewing Riemann surface as two real dimensional manifold. And when I say differential forms, I'll be thinking of function as R to C for and taking fact of Poincare and Hopf and some basic computations and Stokes theorems in differential forms, we get sigma p and c multiplicity of holomorphic invariant for differential is equal to 2g. So these are the basic things we can do on Riemann surfaces. And sometimes Riemann surface can be looked as a submanifold of a bigger complex manifold. And the typical case is algebraic case, where the complex manifold is projective space and we have an algebraic curve on it, in it. So now we'll talk about complex manifolds. To define the category of complex manifolds, we first have to talk about holomorphic functions. And holomorphic functions on Cn, on a neighborhood of Cn, we'll define it as if it has power series expression then we'll say this is a holomorphic function from Cn to C. And we say it's a holomorphic mapping. If you compose it, the projection, then it's a holomorphic function. So it's component-wise holomorphic. Now, complex manifold will be also defined as, so complex manifold will be defined as connected Hausdorff with n-dimensional complex coordinate charts. And the typical example will be Pn, and more typically, we'll be looking at P2. Okay. Now, one result is that smooth algebraic variety, meaning one result is that smooth algebraic variety. One result is smooth algebraic variety is a submanifold of Pn. We know that Pn has a canonical coordinate charge in the way it behaves, and so to prove smooth algebraic variety is a submanifold, so if you reduce it to P2, then to say the algebraic curve, so suppose there's a curve inside, then to prove that the C is submanifold, you have to first show its connectedness. If you can show connectedness, then compactness is a bit, since it's closed, so it's obvious, and Hausdorff is also obvious. Although, I'm not going to prove it here, but there's a result saying smooth algebraic variety is a submanifold. And what do I mean by smooth is that suppose algebraic variety on a complex open set of a projective space can be expressed as a solution of, say, F1 to is equal to n for all the points inside inside the variety. So let's see. It just shows that it just use of implicit function theorem that the tangent space is well defined and like in terms of complex dimension. Okay, one important thing is that we don't really know whether algebraic curve can be embedded in some kind of projective space or there's even a mapping to it. Well, there's one result. So on Pn, consider a function xi, which is the C0. So this is basically on the complex open, it's just a projection, so it's an identity. And if you look at the non-degenerate holomorphic map, and there's a one-to-one with n plus 1 linearly independent meromorphic function. And the map goes like this. So we have a C, P, and C. And this is to map F. Suppose there were non-degenerate map F. Then we can send it to X, I, F. And there are n of them. So there are n of them. And we include 1. The another direction is F0 and 1. And this map is just given by F0. And although like this might not be well defined where like everything is 0, but we know that meromorphic function has a finite order of pole or 0. So by continuation of the singular by multiplying by 0 of order or pole of order or something, then this is actually well defined. And actually this is related to Riemann-Roch also when we consider embedding of curve to some projective space. However, I won't be talking about that. Okay. So now we know algebraic curves are very similar to Riemann surfaces if it's in Pn. And now we'll talk about algebraic curves. Algebraic curves. So actually algebraic curves are defined to be one-dimensional algebraic variety, but we won't go to the what do you mean by dimensional variety? Since it can be like it can be singular, so we can't use manifold definition of dimension. So yeah. First of all, one thing about algebraic curves is that it can be singular. So for example, let's say on C2, we're talking about C2, let's say a variety is given by equation x and y, where this is a polynomial, and let's denote f I x y ith degree components. Then we can express x comma y as fk x comma y up to degree of the curve. Oh, and we also assume f 0, 0. So the variety contains origin. And we will say it has a singularity of order k at the origin. And one thing one can notice is that this will represent k tangent lines. It might be same tangent lines like overlapped, but we can see that with suitable definition the orders make sense. But the intuitive idea is that if you start from kth order, then you can actually compute k tangent lines. And now we define the algebraic curves, and our main focus will be algebraic curves inside P2. So algebraic curves is a solution set of irreducible homogeneous polynomial of three variables. If it's homogeneous, like you can see that suppose we have a homogeneous function. We have a C0, C1, C2. Then multiplying by some number k would just represent like k to the sum d and the original PC0, PC1, and PC2. So the zero order is well defined, and this is how we define algebraic curve on P2. One typical example will be x to the cube minus cx squared plus cy squared. Okay, so it has a affine equation. So meaning when we set to C0, okay, so let's say this is variable z equals 1. And this represents the C2, so the affine equation meaning we intersect the curve with the C2 on P2. We will get x to the cube minus x squared y squared. As you can see, this has a singularity, and so the singularity of order 2, and if you write this, then it becomes y plus x multiplied by y minus x plus x cubed. So on the origin, we have two tangent lines, so, and pictorially, we will do something like this, where there's a singularity of the origin. One result is that irreducible algebraic curves are connected, which I'm not going to prove. And this will ensure that smooth algebraic curves will be Riemann surface. Actually, the more important concept, I would say, is that it's a concept of normalization. So we start with C, this is algebraic curve, and typically we will just say this is in P2. So this is algebraic curve, and we say the pair sigma and C tilde. satisfies three conditions. First, sigma is surjective. First, let's denote S as the singular points on C. Then sigma inverse of S is finite. And furthermore, if we ignore the singular points, so if we ignore the singular points, then this is an isomorphism. See, ignore the singular points. This is isomorphism. So if a certain pair satisfies these requirements, then we say it's a normalization of C. It's a normalization of C. And there are basic results. One form is hard-sort, that every algebraic curve is birational to non-singular curve. And that will ensure like the C delta will always exist for all the C. And on the other hand, I'll take into the fact that for all Riemann surface, so for all Riemann surface, let's say C delta, there exists a curve such that curve anamorphism such that it's a normalization and C has at most ordinary double cones. This result, I'll just take it into effect. The proof will require cohomological methods, and for proving the existence of a normalization will require construction of a variety from function field, like rational function field. And pictorially, the normalization would look like, so we have some, since it's compact, it has to be somewhat like this, and then the normalization would make it into a singular point. It looks something like that. So that's the intuition behind pictorial picture behind normalization. The important thing about normalization is that it helps us to classify Riemann surfaces. So, suppose we have two normalizations, and this would imply that we have an isomorphic of consent, biholomorphic of consents. Let's say U and U. And since these are isomorphism, there's an induced map here. Okay, so this is isomorphic on a very dense open set. And we know that locally it looks like some power, it just looks like a power. But since it's an isomorphism, the power has to be 1. So pictorially we can extend this isomorphism to the whole by such that, like, suppose this is an open neighborhood near C tilde and C prime, where this point represents the inverse image of the singular quotient. Since this is an isomorphism, we can extend the function by just assigning this function and goes this way. Then this will be well-defined and holomorphic. So after all, we can say that if this happens, then we have isomorphism. Due to the lack of the time, I would also won't prove many results. First, I'll consider result, where this represents. So this is all happening in. So this is in P. So we're talking about intersection of algebraic curves, but this is not set theoretic intersection, such as like when we have a tangent intersection, such as this is y minus x squared, then we say you'll have a double intersection. So counting multiplicity, this would equal to degree of polynomial representing C and degree of polynomial representing E. And I'll briefly talk about what's divisor. So divisor is a free abelian group. Generated by points in the surface. So here we're talking about algebraic curves, not Riemann surface. With divisor, I'll be talking about Riemann surface. So this is for Riemann surface. So we say divisor is a free abelian group generated by P and C. Typically it's written as D and let's say it's Mi, Pi, and there are finitely many terms, so let's say I goes from 1 to k. And we say degree of the divisor, degree of D as sigma in terms of I and Mi. With this in mind, we can see that a meromorphic function f will actually generate P and C, a divisor. And so they're like order of P and then we multiply. So for example, if it has in Pi, suppose the order is 2, then it means f has a 0 order 2 near P. At P. And one thing we know that the degree will be 0. And also holomorphic or meromorphic differential will also generate a divisor in a natural way. And also we know that from the Poincare-Hopf that the degree will be 2g minus 2. So it's P omega. Now another result won't be proved. So we have a Riemann. So I'll briefly talk about how the proof goes, but we'll prove it. Riemann curve. So we define ramification. So suppose C and C prime are Riemann surfaces, and we have holomorphic mapping F. Then we define the ramification divisor as before. So we have some ramification index, which is VF P minus 1. And VF here, so we've seen that it represented locally as just a power, so the power is well defined, and this okay, and the result just basically says degree of R equals 2G plus N times NG prime minus 1, where this G is the genus of the first one and G prime is the genus of the second one. And N is the degree of mapping. So what do I mean by degree of it? Okay, we'll consider this as a degree. F P equal Q and V F P. So on the inverse image of Q, then we can define multiplicity, and we just add them all up, and we will say this is a degree. To see that this is well defined, well locally, so suppose P1 to Pn are the inverse image of Q, and it has to be discrete. If it's inverse image of Q, then near P1, it just looks like the powers. Say C to the V1, C to the Vn. Then on the neighborhood of Q, it will be counting multiplicity, the sum will be constant, and since the Riemann surface is connected, this is constant for all the Q values. So the degree is not degree of, and that's the basic logic. To prove this, prove Riemann surface, we actually have to see that this map will actually induce the map between holomorphic differentials. So holomorphic or meromorphic, I'll go with meromorphic. Suppose you have a meromorphic C prime to K C. And this is simply omega to first we do you need to check that this is indeed the holomorphic, this is indeed the meromorphic differential, and that can be done by checking the chain rule. So with this intuition, and knowing that degree of divisor generated by the omega or the holomorphic meromorphic differential is 2g minus 2, with some computations, like lots of computations, you can actually derive this. So this is the intuition, the important fact of proving Riemann surface. And the last result will be the genus formula. The genus formula of a curve at most delta ordinary double points. So ordinary double point meaning the curve can, so graphically you can have like this kind of point, not this kind of points. And I discussed about order of singularity before, and we want the order to be like always less than or equal. So just to briefly explain, like this kind of thing is called cusp, and cusp happens when it's like a square of some kind. If the F2 is like square of this factor, then we have a two tangent line overlap. So together with Bezout's theorem and Riemann-Hertzwitz, you actually get the genus formula for algebraic curves. So algebraic curve, I said delta ordinary double point, so it's not a Riemann surface, so it might not have a genus formula, but we know that the normalization exists. So we're talking about the genus of a normalization of the curve. So let's say genus of the normalization of the curve is actually equal to 1/2 d minus 1, d minus 2 minus delta. And the proof is done by this. So suppose the algebraic curve has an equation of f x y. Then we take a partial f partial y and x y. Then we look at the intersection. Partial decreases the order by 1, so this becomes like d. So this side becomes related to d, and on the other side we look at the projection. So if you look at the projection is actually a map from a curve to a projective space, so P1. Then there we get the genus, and the relation together will give us the genus formula for algebraic curves. And yes, that's it for the algebraic curves. The next, I actually do a quite long proof because I consider it not long proof, but talk about a proof. So to talk about Abel Jacobi theorem, we have to define Jacobian variety. So the Jacobian variety, to define them, we need to know first we need to know the dimension. So the dimension is in terms of complex as a vector space of C. To directly state the result, actually this is equal to G, but I think the proof is quite important. So I won't prove it, but I'll talk about the sketch of the proof. So one side, so for the dimension is greater than G, we use the fact that every surface has is a normalization of a curve at most ordinary double points. So let's say C is the surface we're talking about, and this is a normalization, and this has at most like double points. fix some notations. I'll say C prime. Oh, when I say it's a normalization of ordinary double points, I mean curve on P2. Oh, that I didn't mention, sorry. So when I say there is a normalization at most ordinary double points, I mean the curves in P2. Actually, there's a result saying there's always a holomorphic embedding to P3 and it's algebraic, but that's not the goal. Okay. C intersect C2. Let's say this is zero set of some polynomial f, and say degree of f equal, and let's say gamma is a divisor, and we'll say it's P1 plus P delta, where these are the delta ordinary double points. Oh, and we also have to assume the canonical orientation. So canonical orientation is a C prime. It's not tangent to L infinite. Okay, what I mean by L infinite is C0 equals 0, or you can think of it as P2 minus C2. Yeah. Okay, there's like two viewpoints. It's an algebraic property. And so it's a line at infinity, and L does not has delta points, meaning like ordinary double points, and C prime does not have the point at infinity. Okay. Actually, finding this, so I'll have to prove the existence, but finding this comes with a procedure. So by the Bezout's theorem, we know that any linear hypersurface in P2, any hyperplane in P2, since the plane is given by linear equation and linear equation is necessarily of degree 1, so we know that C prime dot in some hyperplane H is equal to D. And in the generic case, it will be D distinct points. And so let's say H passes D distinct points. H passes D distinct points. Then we just let H equal to L infinite. So then we say let H equals L infinite. And we choose a point on H which does not pass C prime. Then we get C prime. Then we get the point C prime does not pass point. So it's not tangent. It's ensured by, since if it's tangent and it passes D different points, then one of them has to have a multiplicity greater than violates the Bezout's theorem. And it does not pass delta point in the similar argument that delta point has two tangent, then it violates the Bezout's theorem. So this is how we construct the canonical orientation. Okay, back to the problem. And let's say we define S D minus 3 and minus gamma as homogeneous polynomials of degree D minus 3 and such that G of P I basic thing one can get is that, so we want it to be greater than g, so this is how we get the invariant g out. So actually dimension, so this is a complex space, since if it's passes 0, then you can multiply a complex number, and addition is well defined, so dimension of b minus 3 is greater than or equal to, first of all, we define SD3 without any gamma condition, then it has 1 half, combinatorically it has d minus 1, d minus 2. And satisfying the solution meaning at pi, then the coefficients of g, so coefficients in front of the variable has to satisfy some linear equations, and there are at most delta different linear equations, so minus delta, and this is precisely g. So this is the ideal, and what we want to do is construct a map from this to H1C, holomorphic differentials. And this can be done, actually, we've seen that if you have a holomorphic differential, then with some check that this will induce holomorphic differential from to the later on. And from here, we construct alpha in the following way. So let's say we fix g first. So let's say g. So it's a fine equation for g. And we define u0 on, this is on p2 equal the set of points. So the original complex plane, and u1 goes to. One thing you can notice is that this is enough to cover, since c prime does not pass 0,0,1. And we define alpha as follows. So we have g dx partial f partial y on u0. If partial f partial y is equal to 0, then we say g dy and minus partial f partial x. I'll explain why this is smooth in a sense. And in the bottom we have this g 1 over u 3 over u dv. This is on u. I won't go over the proofs, but so first you have to check alpha is well-defined variable function locally, and that's quite easy to see. And to say this is holomorphic, then we just have to check the denominator. And about the smoothness about this, since f x y equals 0 on the curve, we have partial f partial x dx plus partial f partial y dy equals 0. So then the equality makes sure this is somewhat smooth. And this can be checked directly, and with many computations, focusing on if it has a pole, then the denominator has to be 0. And with using these assumptions, we can actually prove that if it has a pole, then it has to be tangent. Then we can be done. So that's the intuition. So although this is a very general theorem, using algebraic method, very explicit computations, we can actually prove this very general theorem. And I think that's very powerful. Another side is less than G. This also I will prove directly. But I'll just state how the proof goes. So let's say gamma 1, gamma G, actually 2G forms a basis of the homology group. And I'll state some results. Suppose integration on some differential, it's not holomorphic biomorphic, it's a differential, equals 0 for all I, then lambda equals f. And actually you can actually construct f as just f p equals, for some fixed point q, you just integrate along any path connecting b and q, then from the homology class is all 0, we can actually prove that this is well defined. Okay, so this one. And another result. Another result is that if you have omega and phi in the holomorphic differential. Oh, and okay. And suppose omega lambda is exact, so some df for some f2 for f some c infinite function. Then what we have is omega. This both results are from the book Griffiths. Okay, so for the proof of this, so this was fairly simple. Proof of this goes like we consider looking at the wedge product. We know that wedge product, not with conjugate, they will give us some kind of absolute value, and if you integrate for the surface, then it has to be very tangent. However, from the Stokes theorem, we know that this has to be equal to 0, and we lead to the contradiction. And so, why is this provable? We have this and is equal to adding 0, and we say 0 is hat omega. And from this, now we have this wedge df. this is the intuition behind proving this theorem. So like together, we can say if you can find omega and phi such that it's like 0 for all of them, then it has to be 0. So okay, together what we have is if you can find omega and phi such that omega plus phi at integration over homology class is 0 for all I, then we gotta, then both have to be 0. Then we use a linear algebra argument saying like omega and phi is non-zero, and we can find such a thing if the dimension is greater than g. That's how it's proved. And with the similar proof, okay, we can define pi I, which is homology class gamma I omega 1 gamma I omega g. So this is a vector in CG. And the result is that pi i's are linearly independent. Okay, now we can state the Abel Jacobi theorem. So first, we know that dimension of the holomorphic differential is equal to g, and what we can do is that from topology we get gamma I, so these are the bases for the homology group, and omega is for the holomorphic differentials, and we take the integration over this, then we get 2g vectors, and 2g vectors are linearly independent. And from this, we know that pi I span a lattice. Suppose this is a lattice spanned by pi I. Then we can construct c to the g and quotient with giving a topology as a quotient topology and coordinate chart as a canonical projection. Then now we define this Jacobian variety JC. Okay, now finally I can state the theorem. Meromorphic function field considered as a group, and the group operation is multiplication. And as you have seen, we can take a divisor, and we know that the degree of the divisor is 0, so div 0 is the divisor that has a degree of 0. And from here, we have a map, and we'll call it U. Actually, U, later on we'll see U depends on Q, but the theorem I'll use won't depend on Q. So we see, and this, so the result is that this is so the first map is taking the divisor. We know this is abelian group and taking divisor, so it's easily seen that it's a group homomorphism. And suppose we have some divisor, and let's say we will focus on P, and P will be sent to, okay, let's just say D. And D, let's say D equals sigma and it has to be finite, but I'll just say I. Then U map is the D goes to sigma n I p I q. So q is a point on a surface, omega 1 up to sigma n I duration omega g. Okay. Well, we first have to show this is well defined. And they can be shown by, what do you mean by integration by q to pi? Then we can show that, so suppose you have q here and p, and there are many different paths. But then the difference of it will be modded by pi I. Why? Oh, because if you have a two path, then so if you have a closed path, then we know that the closed path has to be equal to some boundary of open set plus some homology class and gamma I. And we know the integration of this is 0 by the Stokes theorem, and for the sigma, we know that the Jacobian variety is modded by the lattice, so this map is well defined.